Okay, sorry, this is new to me. I had to figure this out. This is quite fascinating. I'm sitting in front of a computer, talking to the computer, and apparently there are 187 people in the audience listening to me. So thank you. I thank particularly those that have emailed me that they will be here. That makes me feel a little bit better. Not quite as crazy as talking to the screen. So as Boya just said, I've been working on a lot of network-tight arches lately. And so here I am, and I thought I'll tell you a little bit what I've learned over the past 12 years. We'll begin with this picture. This is Per Tveit, the father of the modern network-tight arch. He studied the system in the late 50s and early 60s for his thesis. And he also has a few nice structures to this credit here. This one here, the Bolstad-Straumen Bridge in Norway that he has designed. He's now in his 80s, but is still very active and bugs me regularly to write papers for him that he can put on his websites here, which I've listed down here. He's collecting information about network-tight arches worldwide, and there's a wealth of information on these two websites I've listed. Just type in Per Tveit and network-tight arch, you get there. And so it's a collection of research papers, of practical problems, practical completed projects, and interesting details. Here's another network-tight arch that was also constructed during that time, 1960s. It's not a Per Tveit design, but it's probably inspired by him because he was in contact with the engineers that designed this one. This is the Fehmarnsund Bridge in northern Germany. And I will use this to illustrate what a network-tight arch is. A network-tight arch is characterized by the set of inclined cables. You can see here two sets of cables in each cable plane. So instead of vertical, like the conventional tight arches, they're inclined. And the crucial part of the definition, Per Tveit, is that some of these cables have to cross at least two other cables. So if I take, for example, this cable here, and that's actually been crossed by 1, 2, 3 other cables. So that's what makes a network-tight arch a network-tight arch. You can see this one was built also in the 1960s, and then it has been very quiet for a long time until really the 2000. There have only been a handful of network-tight arches being built worldwide, none as far as I know in the United States. And then over the past 12 years, there has been quite a flurry of activity with regard to network-tight arches. And I know about a dozen by now that have been designed, constructed. HNTB, the firm I work for alone, has completed 5 designs at least, and I know of one more that's in the works right now. If I just want to identify those on the screen here, starting on the west coast, this is the Happy Hollow Park and Zoo pedestrian bridge. It was opened in May of 2011. In Kansas, there's the Earhart Memorial Bridge that was opened just last December 2012. And then if you're going east, there's the Blennerhassett, that's how it's pronounced, Blennerhassett Island Bridge that was opened in June of 2008. That runs over the Ohio River between West Virginia and Ohio. North of that, and just south of New York City, that's the Portal Bridge. That one is not built yet. It's actually waiting funding. We just completed the 100% drawings for that one. And then far north, the Lake Champlain Bridge over Lake Champlain between Vermont and New York. I've been personally involved in 4 of these, so and in the presentation now I will reference the 4 that I know best, of course, mostly. So let me just run you through this, starting in the upper left corner. Here's the Blennerhassett Island Bridge. That's an 878-foot span, 100-foot wide. This is Blennerhassett Island. As far as I know, this is the longest span bridge in the world if you stick with the network-tight arch definition. You can see it very nicely. We have the inclined hangers, and each hanger crosses another hanger at least twice. There are longer span bridges in the world where the hangers don't cross. They're still inclined but don't cross, and Norfolk Coupling Rotterdam, for example. On the other extreme, we look at the fairly small size bridge. This is the Happy Hollow Park and Zoo Bridge. This is actually twin network height arches. The photo is taken from one that's coming out of the picture here. And here you can see the pedestrian bridge, 270-foot span, 13-foot deck, which is designed just for pedestrian and light maintenance vehicle. Lower left corner, that's the Lake Champlain Bridge that was opened in November of 2011. That's a 400-foot span just for the arch, and then 480-foot span between piers, carries 2 lanes of traffic plus generous sidewalks. And then on the high load end, this is the Portal Bridge. This is going to be a railroad bridge designed for 2 Cooper E80 loads. These are very heavy loads. This is about, I did the numbers yesterday, it was like 8 times the normal, or it's about the equivalent of 20 lanes of highway loading. So this, if it gets built, is probably going to be the highest loaded network tied arch in the world. So why do we build network tied arches? I want to start out with just going a little bit over the structural system and showing you the advantages of this network hang arrangement. And to do that, I have this comparison here of 2 network tied arches. You can see in the upper picture a conventional network tied arch with vertical hangers, and in the lower part of the picture you can see a network tied arch with the inclined hangers. The only difference between the two is the inclined hang arrangement. They have exactly the same member sizes, exactly the same quantities. All I did was split the vertical hangers in 2 and incline them with 30 degrees against the vertical. And I will compare these 2 systems under this loading combination that's indicated in the upper left corner. So this represents live load over half the span. So there's some lane load and some truck load. And the crucial part of this is that it's only a partial load, which structural engineers among you know, arches are very, very efficient under uniform load, but they kind of fall apart under partial live load and pick up large bending moments. And the other thing I want to compare here is what happens if we lose, or if the tie girder is damaged. The tie girder is the horizontal member. My pointer doesn't work apparently. So we have the horizontal member, that's the tie girder, and you can see I've introduced a hinge in both of these, and the hinge represents partial damage to the tie girder. Network tied arches, the tie is fracture critical. That means if we lose the complete tie, we lose the bridge. So the tie is crucial to sustaining the load. You can imagine the arch wants to spread out under the weight, and then the tie holds it together, but no tie, the arch will just collapse. Now, what I'm interested here in this comparison is what happens if the tie is only partially ineffective, say a plate has fractured or something. And so we still have the axial load capacity, but we don't have the bending capacity. So let's begin with a comparison of the deflections. And here we go. In the upper picture, this is again just under this live load. Upper picture, L over 300, 36 inch of live load deflection. This is a study we did for Blennerhassett Island. So and this actually drove us to the network hang arrangement, because if you look at the same structure, exactly the same quantities, only the hangers inclined, the stiffness goes up by a factor of 11. The live load deflection are reduced by a factor of 11. So instead of L over 300, we now have L over 3200, or 3.3 inches. So tremendous stiffness increase with very little effort. In the next slide, here it is, I look at the bending moments. And we'll start out with the bending moments in the system with the vertical hangers, conventional tied arch. You can see this is again under the partial live load range, and you can see in the upper picture, if you remember these bending moments, 22,000 kip feet, 32,000 kip feet in the tie girder. And the lower picture shows what happens when we introduce that hinge that represents a damaged tie girder. And you can see how the arch rip moment almost doubles from 22,000 to 42,000 kip feet. And so the bending moment that gets reduced in the tie girder, you can see that also in the lower picture, gets essentially dumped in the arch rib. And of course the arch rib also is a compression member, so we have significant compression forces, so we have all kinds of associated moment magnification issues. Now, okay, so remember those moments, 22,000 to 32,000 kip feet. We're now going to the network hang arrangement. And in the network hang arrangement, you can see the moments reduced by a factor of 5 to 6. So in the upper picture, we have the system without the hinge, with intact tie girder. And then furthermore, if we do lose the hinge, if we do lose a part of the tie girder, nothing happens. We simply reduce the moment in the tie girder, but the moment just gets redistributed through the hangers. So we now have a system that's very resilient to this tie girder damage. The next concern I want to look a little bit is what happens if we lose one of these hangers. These hangers are usually high tensile elements, and what happens if we have to replace one? That's the easy load case, but also what happens if one is suddenly removed, say due to impact, vehicle impact or sabotage. And what this picture indicates is the problem is that we not only lose the hanger, so we don't have the force pulling up the tie girder, but we also have a dynamic effect, and due to the dynamic effect, so the hanger force is removed suddenly and then it overshoots, and so we actually have a force pushing in the opposite direction. It's usually beneficial to do some kind of time-dependent analysis, but here just to show you the bending moments that we get in arch rib and tie girder due to this hanger loss effect. In this next slide here, I've done a hanger loss analysis. This is for the portal bridge. That's the one with the railroad, carrying railroad. And what you see here is the front plane of cables has been removed, so you can only see the rear plane of the cables. They're actually in the structures just for this, to make the view a little bit clearer. It's just in visualization that it's removed. But what has actually been removed are the 3 cables that you see missing in the back plane. So those cables are not there. Instead, what is applied is the force, the equivalent force. So right now the forces are pulling the arch rib and the tie girder together, just like what the actual cable would do. And in the lower left corner you see the box with that red block that represents time history. So right now these cables are applied in full force, and then when I start the animation, we'll see what happens if the cables get removed suddenly. So here you can see this doesn't work very well over the internet, but let me just try it again. Oops. You can see how the arch reacts, and this was portal bridge, so it's a railroad bridge, and that accommodated loss of 3 hangers quite comfortably. So you can see another resiliency in terms of against the sudden hanger loss. So we have multiple advantages in stiffness, in bending moments, as well as in the behavior under these extraordinary loads. The next few slides, I want to just illustrate a little bit the components that make up a network tied arch. I was having way too much fun with SketchUp here, and so you can see how this happens to Blennerhassett Island Bridge, how that's built up. So begin with the piers. This is a very large bridge. You can see a person, you can see a couple of people in the middle of the pier with the hard heads, so just to give you an idea about the scale of the structure. And on top of the piers, unfortunately my pointer doesn't seem to work with this. On top of the piers you can see the bearings, 4 bearings, 1 on each corner, and then those little things in the middle on top of the piers, those are the wind locks to take out lateral shear forces. In the next picture, I added the tie girders. So those are the longitudinal girders. Then we have the floor beams, intermediate floor beams, and then in the corners are the knuckle joints. Those are very complicated elements. They're quite difficult to design too, because this is where the arch rib, the tie girder, and the end floor beam all come together. And you also have to design for bearing replacement. So the knuckle joint sits on the bearings, but when you have bearing replacements, you actually have to put in some jacks to lift, to take the load off the permanent bearings, and so that's another tricky load case that exercises the end floor beams quite a bit. You can see in the inset, those are the actual knuckle joints. Again, to give you a scale, those knuckle joints are just the inside of the tie girder is 7 feet tall. So you can see what looks tiny in the renderings. It's actually a huge structure. You can also see at the end of the front knuckle joint, you can see those gray patches. This is where the end floor beam is bolted into the knuckle joint, and needed a lot of bolts just to transmit the jacking force when the jack is applied. So very, very complex joint, but it's crucial for the structure. It's also through that joint the arch rib gets stabilized a little bit. Okay, next stage, I've added the bracing. This is the lower lateral bracing, so that serves as a deck bracing during construction stages. And in our case, the bridge is very wide, 107 feet center to center of floor beams. And so to prevent lateral torsional buckling of the floor beams, the bracing system actually engages the top flanges of the floor beam and holds them against the lateral torsional buckling. Next stage is adding the stringers. Here they are. So we have the stringers. You can see better in the photograph in the bottom right. And then I'm also showing the arch rib. And then we have that diamond bracing. I like the diamond bracing for these network tight arches because they complement the network hanger arrangement very nicely. You can see it looks nice. It looks pretty good. That theme of diamonds and network. Here's the rendering. So the hangers have been installed, and then final stage is to place the deck concrete. So here we have it. So this is to give you an introduction of what makes up a network tight arch. We like it as an alternative to truss systems. That behavior I've described earlier, the great stiffness, is characteristic of truss structures. But unlike truss structures, we also have the redundancy that we can afford the loss of a few of these hanger elements, which with a truss you could not. I have mentioned earlier that the tie girders are fracture critical. That means if we have damage to the tie girder, if we lose the tie girder, that's bad news. So we try to improve the redundancy of the tie girder so that we have alternative load paths. So I will talk about that a little bit in the context of the various deck systems. Let me start out with a cross-section of the Blennerhassett Island Bridge. The Blennerhassett Island Bridge used a concrete deck that was separate from the tie system. So you can see it in this is the cross section of the floor beams. So we have a box-shaped tie beam, and then the deck is a stringer type construction. The stringers sit on sliding bearings on top of the floor beam. And so that has an advantage and a disadvantage. The advantage is that the deck, the concrete deck and the stringers are not part of the tie girder. And the disadvantage is that the deck and the stringers are not part of the tie girder. So we're giving up redundancy, but we keep the deck free of tensile stresses from the tie girder action. Now, we can do something to the tie girder to create internal redundancy. This is usually referred to as a stitched cross-section, and it's illustrated in this slide here. So the tie beam is made of 4 individual plates. They're just bolted together in the corners, as shown in the left picture here. And the structure is actually designed so that we can lose any one of the 4 plates, and the tie girder is still functional. This is where the ductility or the insensitivity to bending moments comes in too, with the network tied arch bridge. So we can afford, we don't really need the moment capacity of the tie beam with network arrangement. Now the idea of the bolted connection is that if any one of the plates fractures, that fracture would be arrested at the bolt line, and so we would not have a progressive fracture throughout the entire cross-section. It's a pretty expensive approach to do these bolt lines. It's for example, in case of Blennerhassett, it added 140,000 bolts to do this. In Europe, they don't do this. They just build these things, but it's kind of considered cheap insurance. So this is a very common detail in the US. One other thing I want to mention, that is the connection of the floor beam to the tie girder, and you can see this in this picture here. So what you see as a top view, you see the tie beam that's painted in the top. You can see a floor beam and the lateral bracing framing in. And typically, these floor beams are only connected with shear tabs and don't have the flange connection. But that often leads to fatigue issues because the tie girder wants to move and the floor beam and the deck want to move differently. And what you often see is that the web at the floor beam cracks due to deformation-induced fatigue. And the other problem or the other advantage, so let me put it this way, so for that reason we connected the floor beams to the tie girders, and it had another advantage, which is with these long beams that are sensitive to lateral torsion and buckling. By holding the floor beams near the ends, we actually improve the lateral torsional buckling resistance of these floor beams. So that is one approach where we have the stringers and the deck separate for the tie girder. The other extreme is shown here. This is the Happy Hollow Bridge. If you remember, that's the pedestrian bridge in San Jose, California. And what you see here is at the right edge where the cables are attached, there's formwork, so the wooden thing, this is formwork for the deck. But then you can see just the top of the tie girder. This is a small bridge, so the tie girder is a lot smaller than what we've just seen for Blennerhassett Island. It's just a WT section. So that's one line of defense for our tie force. But then in this case, the deck is integral with the tie, and so we have multiple levels of load path. You can see in white shown are post-tensioning tendons that run through the deck. So they keep the deck in compression even when it acts as a tie girder. And then it also serves as a backup load path in case we lose the tie. And then on top of that, we have also plenty of rebar in the deck, so there's another level of redundancy. The rebar alone can take a good portion of the tie force. So we really have 3 tie girder systems at Happy Hollow. The tricky part here is to make for clean load path near the knuckle joint. You can see this is the knuckle joint for Happy Hollow, significantly smaller than the Blennerhassett Island Bridge knuckle joint. I think these are 1 inch or 1 1/4 inch diameter bars, just for scale, so a much smaller system. Now you notice the plate with the shear studs, and then you notice the vertical plate at the right end with the openings. The openings are there to allow access to the post-tensioning tendons. You see 4 post-tensioning tendons and 4 openings. But then you have to transmit the thrust that's coming down from the arches, and you have to get that over to the tie girder. to the tendon, to the post-tensioning tendons, and that's what that shear stud plate accomplishes. The bars with the nuts, they're actually there for bearing replacement. When you have bearing replacements, we place jacks just inboard of the arch rib, and that creates a huge moment gradient, and the nuts are needed to develop the rebar more quickly through that knuckle joint here. And this is a view of the deck of the Lake Champlain Bridge, and this used a similar scheme as the Happy Hollow Park and Zoo Bridge. What you see here is the deck panels. There's a transverse joint. You can see the post-tensioning tendon, so similar to Happy Hollow, the deck is post-tensioned longitudinally. Here, precast deck panels were used. That is advantageous when you support your deck on steel stringers, because you take out some of the creep effects. And so this system has more redundancy, because now we have the deck, the tie girder, and the stringers are all participating in the deck load path. Okay, in the next session, we'll talk a little bit about hangers and the connections of the hangers to the arch rib. And I begin with the traditional system. This is Happy Hollow again. Very small cables in this case. These are 3/4-inch wire rope or bridge strand cables. And you can see it makes for very, very simple connections. So the arch rib in this case was an iron girder turned on its side. And all you need to do is just weld the plate in and then pin connect the cable to that plate. At the lower end, shown on the right-hand side of that picture, you can see some turnbuckles to adjust the cable forces. Very simple operation. In this case, for some cables, they didn't even have to unload the cables. They can just turn the turnbuckles. For the highly loaded cables, you'd need to come along, unload the cables, and then turn the turnbuckle. But very quick and simple connection. This also works for the larger size bridges, and this is really the traditional method of hangers in the US at least. You can see this is the Amelia Earhart Memorial Bridge. Disregard the junk in the front. These are the older bridges, and what you see is the ribs of the new arch bridge in the background. You can see the cables are about to be installed. So these are, I think, like 2.5-inch diameter bridge strand or wire rope, and in pairs. So now on Blennerhassett, which is coming in a second, we borrowed some technology from cable stayed bridges. So instead of the traditional wire rope, we used a bundle of 7 wire strands. So these are individually sheathed and greased strands. They're, you can see in the right-hand picture, they're made up of 7 roughly 1/4-inch diameter high-strength steel, 270 KSI steel. The sheathing and the greasing is there for corrosion protection. And then on Blennerhassett, we had 27 of those in the bundle. The whole system is encased in an HDPE pipe. And you can see in the lower left corner, this is a view of the anchorage. You can see the strands running into the anchorage. They've cut away 1/4 of the anchor. And then they're anchored with wedges in an anchor plate. So similar to a post-tensioning strand. The whole anchor assembly is threaded, and there's a ring nut to adjust the whole anchor. And in the upper view, you can see the transition. What's crucial with this system is to maintain the corrosion protection. So you have the nice sheathed and greased strand for most of the length, but then in the anchor region, you have to strip the sheathing and flare the bundle out so that it can be fed into the anchorage plate, and the strands have to bite directly into steel. So you'll see later in this presentation there's some very fancy devices and means to really make sure this is watertight. Now these systems can be strained as a whole, But the advantage is that the cable can be stressed one strand at a time. So that's the difference to the bridge strand, is the one strand at a time stressing. The Post-Tension Institute has published pretty extensive guidelines for design and testing of these stay cable systems, and Blennerhassett Island was subject to the same type of testing. So what they do is that the cable gets tested 2 million load cycles to a fairly high stress range, and then after the fatigue test, one of the cables is stressed to failure, and another one is submerged in 10 feet of dye, of water with dye in it. And it's nasty stuff. You can see it in the 3 pictures on the right hand side. And it has to sit there for several days, and then after several days the anchorage is disassembled, and in order for the test to pass, none of that dye can reach the strands. You can see that in the bottom right hand picture where you see the openings for the strand, but the dye has not penetrated. This is, by the way, this is the test that was confirmed for the Lake Champlain Bridge. Now with these multi-strand system, you need access to the arch rib, and here's the uphanger connection for Blennerhassett Island Bridge. So in the left picture we have a view up the arch rib, and on the right side there's a cross section. It was 5'6" by 4 feet wide. It's pretty snug. It's doable, but it's getting tight there. You don't want to be much less than 5 feet deep, or you, to fit your system in and to be able to install the wedges. But you can see in the left-hand picture, you can see the anchor beam, you can see the ring nut, and with the threads, you see the anchor head and the gray cylinder on top of the anchor head. That's the cap that protects these strand extensions from corrosion. So it's a well enclosed system. And that can be installed with very light equipment. Here's another view, or a view of the bottom anchorage. This is also Blennerhassett. In the left, this is a rendering, because usually people get very nervous when you tell them you want to stress these large cables from inside a box. Blennerhassett was actually quite generous with 7 feet by 4 feet. We'll show you Lake Champlain in a moment here. So the left is a rendering where we tested out the equipment, and the right is with the strands installed. Now the cable runs through the upper flange. You can see that here. This is the top of the tiger in Blennerhassett Island. You can see the guide pipe running through the flange. Then the flange connection, the bolted connection, is where a damper was sitting for vibration control. We only used that on Blennerhassett Island because it was longer cables than the other bridges. And then sitting on top of that is an anti-vandalism tube. So that's a tube that just protects the cable in the lower portion, but we don't want to have HDPE pipe exposed to the traffic. Strand installation and cable installation, as I mentioned earlier, is done with very light equipment, one strand at a time. So here we are on the barge. The lower insert shows that's one strand is installed. That blue device is just a collar to hold up the anti-vandalism pipe. You can see in the larger picture, you can see the cable with the anti-vandalism tube, and then transitioning to the HDPE pipe. So the whole thing gets lifted in, one strand plus the HDPE pipe, and then the next step is just one strand at a time is attached to a little winch system. The strand is pulled up inside the pipe, and then a worker inserts the strand through the arch rib, through the wedge. Upper wedge is seated, lower strand is stressed. I promised you a picture of a much more constrained site. This is inside the Lake Champlain Bridge, which was only, I think, 4.5 foot deep. You can see the very light stressing equipment that is sufficient for this strand by strand installation. Now it is possible to stress the whole bundle. Now if you do that with the full force, the jack gets very heavy, so you don't want to do that. But during early installation stages, often you have to pick up the whole bundle, and you can do that with a light system where you have multiple smaller jacks, and they bear against a reaction plate. This again is Blennerhassett. You can see in the left picture in the foreground, you can see a threaded tube and a reaction plate. In the right picture, they're screwing it onto the anchor head, and then they had 4 individual jacks. And so that was used to just yank on the cable ones to seat the upper wedges properly. In the insert, that's actually the one that was used on Lake Champlain Bridge. Lake Champlain, by the way, was kind of a hybrid between the pinned connection with the traditional cable, with the traditional wire rope, and the strand by strand that we use for Blennerhassett. On Lake Champlain also has an I-shaped arch rib, similar to what I've shown for Happy Hollow. So we didn't really have room to seat wedges and to have anchor beams in the arch rib. So there, the idea is to prefabricate the whole cable in the yard, and you can see the cable being assembled. Lake Champlain only had 7 strands per cable. So in the middle of the picture, where the 2 workmen are active, you see him with the hammer. He's just seating the wedges at the end. You can see the anchor plate with threads, and then these 2 assemblies. They're there to seal the system against moisture intrusion and to hold the pipe in place. So they can squeeze the whole. This is a neoprene collars, and they squeeze the neoprene collars together, and that expands the system, that ensures water tightness and proper seating. In the foreground, you can see a machined and a piece, or actually a cast piece, pin piece, and that will be threaded on the thread of the anchor plate. So in this next picture, you can see it's been threaded on and filled with a corrosion inhibiting grease. And here's the assembled cable, actually 2 side by side. The one that's currently being picked up, that's a very short one near the ends of the arch rib. So you can see we have the pin, we have the anti-vandalism where that yellow sling is just long around, and then we have the rebar and the lower flange plate where it's connected to the tie girder. So this is a very tiny one. The one in the foreground is more typical, where you just see the upper anchorage. And then the final step is the whole cable is lifted in place, as shown here. And then it's very simple pin connection, just like what you've seen for the Happy Hollow Bridge. So with this system, much less work for cable connecting, but you need much larger equipment to stress if you have large cables. And of course you have to deal with the weight of the cable, and if you have to replace the entire cable. With the strand by strand system that I've shown earlier, the multi-strand system, you can actually replace 1 strand at a time. So pretty much if you have large arch rib and large cables, you want to go with probably the multi-strand system, and if you have smaller structures, you're better off with this pin type connection. The last step is to prevent the cables from slamming against each other where they cross over. So this involves installing of a cable spacer. This is a view of Blennerhassett, and you can see nicely what I've showed earlier about the bracings complementing each other, the archer bracing and the hanger bracing. So it's just simple clamps. One interesting thing though is because the HDPE pipe has about 20 times the coefficient of thermal expansion of the steel, the pipe actually have to slide relative to each other, and so you normally need to provide for pretty good movement range at these cable spacers. Here's another one that we used on plane. This one is made out of HDPE, which is pretty smooth by itself, so that will slide okay. That concludes the connection, and now let me move on to erection engineering hanger tuning. You probably appreciate that with these arch ribs, the problem is that the final structure and the intermediate construction stages are very different, and therefore it's of great importance to make sure that none of these intermediate stages are unstable. And then, of course, with the hanger installation, it's you want to get the cable forces right, and you want to get the geometry right. So reaction engineering takes a very large role in arch erection. I know Steve Percassi is in the audience. He can tell you everything about it because he did a lot of the erection engineering for Lake Champlain. I want to show you this example. This is Happy Hollow network tight arch. This was a particularly challenging structure. And if you just look at the rib dimension, this is a W14 by 109, extremely slender rib, turned on its side. The slenderness ratio of the rib before the cables were installed, so just the rib by itself, was 1,000, kilo-hour of 1,000. So clearly not stable on its own. And then as an additional twist, during erection of this structure, we were not allowed to place false work in the estuary. This is Coyote Creek. This is a heavily polluted little creek running through the site. It got cleaned up by now, but for some reason we were not allowed to put false work into it. So instead, the false work system, is shown in the top picture, it uses cable stay. So the false work system is stayed back and then supports the arch rib from there. So this gets quite interesting because now you have the competing systems. There's the arch rib trying to take one share of the load, and then there's the false work system taking one share of the load. And then also, because the tie was so light without the deck, the cables are not don't have a whole lot of tension, and some cables in fact are slack. And so you have this wet noodle in the sky, the boiled spaghetti in the sky, and you have a very slender arch and flexible false work system. So this was, of all the bridges I've worked on, this was probably most interesting construction staging analysis. For the more typical structures, this is a little bit simpler. Because typically by the time you get to placing the deck, you don't need the false work anymore. This, for example, is Blennerhassett Island with the cast-in-place deck, so you can see the arches erected, the false work system has been removed, and now we'll just go and happily place the concrete deck. So the only thing to watch out for is I mentioned earlier how sensitive arches are to non-uniform loading. So so that's something to look out for, and make sure that you don't get unbalanced load. Blennerhassett was very non-sensitive to that, so they just did it in 3 big pours, starting from one end moving over to the other end. Now the final stage is to get the cable forces and the geometry right. This is during construction, there's so much interaction with the false work and with tolerances and with temperature. You'll never get the geometry just quite right at the end, and the cable forces won't be quite where you want them. So there's always a final hanger tuning stage. So the arch is completed. We're gonna go around and survey the forces. You can do that with lift-off test with the larger cables, or you can do it with a tensiometer with the smaller cables, where you just deflect the strand a little, and from that you can deduce what force in the cable is. And then we go through and have to come up with a cable adjustment schedule. That is, by that stage, the system at least is linear because the concrete is placed, the cables are all highly loaded, so we don't have the sag effects anymore. So in principle, it's not that difficult. It ends up being an optimization problem. If you think about it, this is Happy Hollow, where we have 88 cables, so there's 88 cable forces to adjust. And if you use the attachment points at the tie girder for your geometry, so that's another 88. And if you care about the arch rib geometry, that's another 88 variables. So we have 264 parameters to optimize, and we have 88 cables to pull with. So this is you can create an influence matrix to determine how each unit load case affects the adjacent cables and adjacent geometry. So this is for example, if we look at that first row, the load case PTN03, if that gets tensioned by 1 inch, that particular cable picks up another 20.1 kips, but the adjacent cables pick up compression minus 8.2, minus 4.4 kips. And then this affects geometry as well. So it's a huge analysis problem. It's a huge optimization problem, but nowadays it works quite nicely. In fact, since Midas is sponsoring this, I give them a little plug-in. Midas has a facility that will create these influence matrices for you. They call it the unknown load factor utility, and you can actually do the optimization within Midas. I prefer to do it in Excel using the solver utility, because you can construct really complicated and optimization constraints, and it solves this in seconds. And if you do everything all right, then by the end you have a, where is it? Here we go. So if you do it nicely, if you do it correctly, at the end you get a bridge that's straight as an ironing board, like Blennerhassett, not Blennerhassett, Happy Hollow. You can see the extremely slender deck, very straight cable forces wherever we wanted them. You don't want to be too picky. It's hard to get the cable forces just right, so you don't want to design too close. But the geometry we can get within a fraction of an inch easily. Okay, so now we've done the erection engineering. It's out of the way. Let's look to the actual construction. And as I mentioned earlier, arches are interesting in that the construction stages are very different from the final stage. And I want to run just a few methods. This is the first one, which we call stick building, where each component is simply delivered to the final location and then installed. So here, Blennerhassett Island Bridge again. We got the pier up, we got the in-floor beam up. You see the shoring system or the falsework system. Pieces of tie girders are up, and you see the threatening barge in the background, where I spend many sleepless nights wondering what happens if one of those hits the shoring system, which they never did. These are steel casing, 3/4 inch steel casings. They were filled with sand for a little bit of protection, but the contractor told me the main protection is good insurance. And then we're moving on to the next stage. So here the bridge is erected. This was done by Barge construction. They came up with this erection scheme. Actually, the guy who came up with, unfortunately, passed away. He was a high school dropout, but he's built like 10 of these arches all over the Ohio River. So you can see a nice system. You see the arch rib supports, you see the struts that support the arch ribs, and then you can see the cables that support the cantilevering part of the tie girder. This is an interesting stage because at this stage, if you try to estimate where the center of gravity of the arch is, it's actually outside of that front line of steel casing support. So the whole arch really wants to tip over, and you have to prevent it from uplift. You can see the uplift restraints. So we are looking at the end of the. You can see the knuckle joint in the background, and then the two jacks in the foreground, and the cross beam. They're pushing down on that end floor beam and prevent that arch from toppling over. It did lift up a fraction of an inch, so you could actually see air underneath the bearings. And you see one of there's a backup system, so in case the main set of tie-downs fails, there's a secondary system just for redundancy. Moving right along, so here we have the second half is erected. You can see the shoring system and the channel for traffic to pass through in the middle. And then it gets interesting because now we have to close the two arch halves. And there's always the excitement, will the last piece fit? In this case, the contractors made sure it would by building one of the arch halves about 6 inch off the center, moved towards the abutment. So there was a planned 6-inch gap. And they had a longitudinal jacking system. There were sliding pads underneath the supports where the arch is sitting on the caissons. And so to close the tie girder, they pushed the arch together and until the last tie girder element would fit. Now the arch rib, then the keystone segments for the arch rib, this is where it gets really interesting because they cannot really push anything apart anymore. But what you can do with these struts is to actually shape the opening by moving the struts up and down, and that was pretty amazing. The strut system. I have a close-up view of the adjustment jacks, and you can see where they had a jacking mechanism where they could vary the length of these jacks. So this frame just keeps the two parts of the jack together, prevents it from moving naturally. There's 4 4-inch diameter threaded rods in there and 2 large jacks. And so just by inflating and deflating the jack and adjusting the nuts on the rods, they could adjust the jacks to again a fraction of an inch, 1/8 of an inch, no problem. And here's your friendly strut adjustment group. It's 3 people. The guy in front runs the hydraulic pump, and the 2 guys in the background adjust the nuts. And here are the guys working, actually installing an upper lateral bracing. This is about 230 feet, is that right? Yeah, 230 feet above the river, so they made sure they got extra sturdy platforms for added comfort. And the last stage then is the cable installation. You can see this in this picture. So the crane, they happen to have the heavy crane here, the Ringer crane. But the cable is nothing at this point. It's just the HTB pipe and 1 strand. And then we go to the strand-by-strand installation. Now the other extreme is to build the whole thing on shore and then put the arch on barges and lift it in place. This is the Lake Champlain Bridge. You can see the arch is onshore. You can see the bays at the end. Right now the arch is still sitting on transfer girders, so it's sitting on land. But there's the bay where the barge can slide in, and they're just about to transfer the arch loads from the steel girders onto the barge. And then you pull the barge out with pulleys. By the way, there's a very nice time-lapse video on YouTube. If you type in Lake Champlain Bridge, there's an HNTB time-lapse, very, very good quality that shows all these operations that occurred over a 24-hour period in 4 minutes. All right, so we are moving right along. This, by the way, was done 2 days before Hurricane Irene hit the East Coast, which I thought was very courageous. So here we are approaching the site. The approach spans are done. They have to maneuver the arch in space into place. This is the lifting assembly. So these are strand jacks. So the way this works is it's a hydraulic jack that picks up, lifts 6 or 8 inches, resets the wedges, deflates the piston, resets the rear wedges, jacks up a little. This is how very heavy loads get lifted, and that white assembly is just to keep the strands from kinking, so just to deviate them. This is a tri lift, so this is just dead weight in the front. Normally that operation should go rather quickly. A foot an hour shouldn't be a problem. Should be faster than that. So here we go. The cables are ready to be attached to the arch rib, or to the end floor beam, that is, and we have lift off. And so now the bridge is just hanging from the cables, and here it is. So the bridge is out. So in the left corner, you can see there's still a piece of floor beam underneath. So the final operation is actually to install the floor beam or the support beam that the arch actually sits on in the end. Now the last construction method, this is one I don't have a known project. This I borrowed from a brochure from a contract in Germany, Max Vogel. This is a launching arrangement. They do that a lot in Germany, where so the way this works is the arch is built in line with the bridge, so in the future alignment, but slid over onto land, and then the right side in this picture, this is actually a barge. You can see it very well, and the left side is on land. So when they're ready to slide out the arch, they just push the barge out, the rear end gets dragged along with it, and then they place the arch on the bearings. This is actually a similar scheme we're considering for the portal bridge. And I close my presentation with this last slide here, the last view of the Blennerhassett Island Bridge. I put my email address on here. I'm not sure how this works with questions, but if you have any questions, you can reach me here at my HNTB email address. And that's the end of my presentation. Thank you.
All right, thank you, Gregor, and thanks everyone for attending the session. Just as a reminder, I'm just showing the dates for the following up sessions. So on February 14th and February 21st, we have 2 more sessions regarding the tied arch bridges. Please sign up for them. And also for next month, in March, we have 4 more technical sessions. You will receive the invitation for them as well. If you have any questions, please feel free to contact us, and we'll be happy to answer the question. Thank you so much. Have a good evening.